It's actually been a little while since you guys have had a video. We've covered a lot of stuff in class, and trying to get us moving back forward again. We finished up our linear regression activity. For those of you that weren't in class on Friday, the second page of the activity we started on Wednesday will be submitted for a quiz grade, and I will be grading those this week. So if you don't get them to me soon, I'm going to have to unfortunately give you a 0 on it. So make sure you get those quizzes turned in to me. The notes that we're looking at today is a very brief set of notes. So what I anticipate is that you guys will watch this video Monday, and on Tuesday we'll go over some of the suggested problems and perhaps start the next set of notes, and then again we'll cover as much as we can get through on 2.3, and then I'll just make a video for the remainder. What I'm going to show you guys today, it's going to be heavy with the calculator. So I'm going to show you not just the TI Nspire calculator like what we use in class, but I'm also going to show you the Desmos online graphing calculator that you can use at home so that you can practice these problems without having to worry about having the TI Nspire calculator available to you. So what we're doing is we're just taking data and we're trying to gain a linear model from that data. Everything that we're going to look at for right now we're going to assume is linear so that we can process the steps that I'm going to show you on this set of notes. So we'll just jump right into the first example. It says that in baseball, the on-base percentage for a team represents the percentage of time that the players safely reach the base. The data given represents the number of runs scored, represented by the variable y, and the on-base percentage x for the teams in the American League during the 2016 baseball season. Use a graphing utility to draw a scatter diagram. So the first thing that I'm going to do, I'll do this on the Nspire calculator. Then when we do example 2, it's the same data, but I'll use the Desmos to show you how to do this. So with the Nspire calculator, from your home screen, select option 1 for new, and you want to add list and spreadsheet. Now we have our column X, which is the on-base percentage, and then we have our column Y, which is the runs scored. Now you can label those on-base, runs, however you want to do it. That's entirely up to you. I need to find my keypad here. Sorry. This will make life a lot simpler. Alright, so turn that on. Okay, so in our first column we have 31. Alright, and on the Nspire, remember, like I've told you before, when you enter that last data point, make sure you hit enter. Otherwise the calculator does not recognize the values that you've typed in that last box. So part A just says use a graphing utility to draw a scatter diagram. So we've entered our data, we go back to our home screen, and we're going to select the purple histogram. It's the 5th icon over on the bottom of your calculator, and it randomizes the placement of all the points, but we're going to arrange those a little bit more neatly. Click on the horizontal axis where it says click to add variable. We're going to add our X value, and then on the vertical axis do the same thing, except here we're going to add our Y, and there is our model. So part B is just an interpretation of what we see based on this model. This does appear to be linear, and it says describe what happens to runs scored as the on-base percentage increases. Well, it makes sense. As the more times a player is on base, the higher the probability is that they will score, or that the team scores a run. So as run scores increases, the likelihood, or as on-base percentage increases, the likelihood of scoring a run increases as well. And that's all you have to indicate for part B. So you can just write that down, and that's the end of example 1. That's all you have to do. So for example 2 and 3, which we're going to get to now, really I want to point out that the points on our data are not perfectly linear. They're not exactly all on the exact same line, but we can see why they would tend to be trending towards a linear model based on the shape of the data. And we can look at scatter diagrams and we can come up with whether or not that data represents a linear or non-linear function. And we're going to do that here in example 2. For example, or for part A in example 2, this does appear to be linear. It has a negative slope, but it does appear to be linear. So we will say yes, this is linear. For part B, this looks like a U shape almost, so we're going to say that is most likely quadratic, so it is not linear. I know this question doesn't ask you to describe it in that kind of detail, but this is definitely probably a quadratic model. And then part C, we have this kind of funky curve, which does look like a cubic function. So this might be a cubic model. And then our last one here kind of has this J shape to it, and that most likely would be an exponential. If you happen to be following the news lately, I was looking at a graph for the spread of coronavirus in the US, and it is exponential. That's the curve you see there on the end for part D is very similar to the curve that I saw on the graph that demonstrates the spread of the coronavirus in the US. One thing that's interesting to note is that the curve that represents the spread of the virus in China is what we would call logarithmic. It actually started out, I know I'm getting off topic, but it's still kind of interesting. The curve started out, it looked like it was exponential, but then it reaches a point where it kind of carries over like this, and it reaches this point where it's not spreading as rapidly anymore, and this is what we would call a logarithmic curve. You see that a lot with say, for example, wildlife studies when you're looking at say deer population in eastern Kentucky. The carrying capacity for the land really kind of dictates how large the deer population can become. If the deer population exceeds the available resources for food, then you're going to notice a very rapid die-off of the deer population. So this logarithmic growth kind of is indicative of what you see with wildlife populations. And in this case also with the Chinese spread of coronavirus. It did start out exponential, but it has tapered off as far as a rapid growth, and it's logarithmic. Anyway, so enough of my inane ramblings. Example 3, we're using the data from example 1, and it says part A says use a graphing utility to find the line of best fit that models the relation between on-base percentage and run scored. Interpret the slope. Part C, use the line of best fit to predict the number of runs the team will score if its on-base percentage is 34.1. So real quick, go back to the TI Nspire. We've done this before. You should have done this on Friday with your model when we were talking about the Monopoly game. But here it's real quick to come up with the line of best fit. We go to Menu, Analyze, Regression, and we select Show Linear MX plus B. And there's our line of best fit. The equation that models that is 48.805x minus 834.993. Hopefully when I do this with the Desmos, we're going to come up with the same value or approximately the same model. And I'm going to show you how to do that now with Desmos. So you want to go to desmos.com, DESMOS, and it's a free online graphing calculator. You can do a whole lot with these, this is especially useful if you don't have a TI Nspire at home or a graphing calculator at all. With this calculator, you can do almost the exact same things that you can do with our Nspires at school. So here on the left is where you have kind of your entry pad, and then on the right is your graph screen. So what you want to do, since we're going to type in a table of values, is go to Add Item, and we want to select Table. So we have X sub 1 and Y sub 1. So again, this is going to be the values that we had in example 1. So I'm going to type those in again on this screen. All right, so all the values are entered, and we should expect to see our points on the right hand side of the graph, but we don't see those right now. So what I want to do is maybe click on graph settings. Okay, that's not going to work. Let's try this. I know there's a way to come up with these values. I have to flip my keyboard over here. Okay, so there's our points, colors, good. Okay. So what we need to do is adjust our viewing window. I thought there was a way to do that where it would zoom in on. Guess there's not. So I'm just going to zoom out by scrolling the mouse pad, and now we can see that data that we typed in. There's all of our points. Now the graph does look different than what we had on our calculator, and that's simply just because of the scale that we're looking at. If we use the exact same scale that was on the Inspire, then the points would be exactly the same. But what we want to do is create the line of best fit, and to do the line of best fit, you would just type in Y, use the underscore key to bring in a subscript, Y sub 1, and then we want to use the little tilde symbol. So Y sub 1 tilde, which means it's approximately MX sub 1 plus B. So Y sub 1 is approximately MX sub 1 plus B. And you can see in the bottom of this screen right here, it says our parameters. M is 48.8054 and B is negative 834.993. That's the only values you're interested in, because you'll substitute those in to generate your equation. So you replace M with 48.805, B with negative 834.993, and you've generated your line of best fit. One thing you may want to look at is this R value, where it says R is equal to 0.9399. The closer that value is to 1, the stronger your model will tend to be. So in this case, we have a very strong model with a R value of 0.9399. So we will go back to the calculator, and you can see the values that are on the calculator are exactly the same as what we came up with Desmos. So we're going to use this model to finish out example 3. And let's see, I need to write that equation down. Okay. So I'll go back to our screen here. And for part A, that will be the equation. So it's Y equals 48.805 X minus 834.993. And it says to interpret the slope. So what that means is, as the on-base percentage goes up, for each percent that the on-base percentage goes up, our runs scored should increase by 48.805. So that's exactly what that interpretation is. So as on-base percentage increases, the run scored increases by 48.805. And then finally, part C, use the line of best fit to predict the number of runs a team will score if its on-base percentage is 34.1. So here we want to go to our calculator. I'm just going to use the Desmos calculator. 34.1, I believe, is what it was looking for. So we can just click right here on a new line, and we can type in, what is it, 48.8051 times 34.1 plus, or no, sorry, that's minus 834.993. So we should expect the team to score 829, roughly 829 runs in a season where they have an on-base percentage of 34.1%. 829. I'll write that down for you. So 829 runs. And that's it. That's the end of the notes. Like I said, these are fairly straightforward. Should be pretty simple to complete. You have only 2 problems to do for the suggested problems. So if you want to save those for class on Tuesday, we'll discuss those, and then we will go over, begin going over 2.3. Hope you guys have had a great weekend, coronavirus free, and I will see you in the morning.